Welcome to the next installment of the PowerPoint lecture series for AP Physics B Introductory Information. Today we're going to be talking about vectors, what they are, how we draw them, and some examples of different types of vectors. So the topics that we'll discuss: what vectors are, how we draw them, how we represent them on paper, vectors versus another kind of quantity that we use in physics called a scalar, and also typical examples that you'll be seeing in this class. Vectors are defined as physical quantities that have a magnitude and a direction. Now, it's important to understand exactly what magnitude means because a lot of students have confusion about that when they first start out in physics. Magnitude means only this, that the amount and the unit that is associated with the quantity. So, for example, if I say that that my car is going 10 meters per second to the east, the magnitude of that velocity would be 10 meters per second. That's all it means. Direction is the other part of what a vector has, and this direction will indicate which way the vector is pointing. So up, down, east, or west, depending on the coordinate system that you choose. You could say it's along the positive x-axis, the positive y-axis, for example, and that would be your direction. So in this previous example, my car has a velocity of 10 meters per second east. The magnitude again would be 10 meters per second. The direction would be east. And I have another example here. My cat's velocity is 5.5 meters per second north. Again, the magnitude is going to be 5.5 meters per second. And the direction would be north. Vectors have a specific way of representation. Vectors are drawn as arrows. They look like arrows with a tip, the arrowhead, and a tail, a line. So this would be your vector. This would be the tip, sometimes called a head. And this would be the tip. The tip, the arrow, points in the direction that the vector should be pointing. And then the length of the line, the tail, is going to be proportional in scale to the magnitude of the vector. So for example, if I draw a vector that represents 5 meters per second velocity to the east, I might draw it like this. And if I wanted to represent another vector that was twice the magnitude, or 10 meters per second to the east, I would just draw it twice as long, but pointing in exactly the same direction. When we're drawing vectors, the first thing you want to do is to define your coordinate system. Is it going to be a Cartesian coordinate system, for example? Define that first, and then draw your vectors with respect to that coordinate axis. So you can draw a vector as a line with an arrowhead pointing to the right. Depending on your coordinate system, this could be along the positive x-axis, for example. You can also draw a vector pointing in the opposite direction with a smaller magnitude. Vectors can point up or down. Again, if this was on a Cartesian coordinate system, this would be along the positive y-axis. You can also have them pointing downward along the negative y-axis. Draw them diagonally at an angle with respect to the positive y-axis, for example. And then finally, these kind of weird-looking representations you'll see sometimes. This represents a vector that is pointing outward. Pointing outward at you, pointing outward from the board, pointing outward from the page, and this x represents a vector that's pointing inward. Inward toward the board, inward toward the page, inward toward your desk. For example, one way that people like to think about this is that the dot kind of looks like the tip of an arrow coming out at you. And then the x looks like the feathers at the end of an arrow. So you can imagine it pointing away from you or moving away from you. To indicate direction, again, the first thing that's very important to do is to establish a coordinate system. In this class, it's going to mostly be a Cartesian coordinate system with an x and a y-axis, sometimes a z-axis, but not that often. The direction of the vector is generally specified as an angle with respect to the positive x-axis, no matter where your angle ends up on your coordinate system. So if you have a vector that's pointing this way, you're going to specify the angle, generally we call that theta, as an angle with respect to the positive x-axis. If, on the other hand, your vector is pointing along the third quadrant, we're still going to want to draw the angle and determine it with respect to the positive x-axis. That's just a standard way that we do things. Sometimes in your textbook you'll see it a little bit differently, but in general it's good to have a uniform way to represent your vectors and their directions. How do we represent them on paper? Well, again, I've chosen a coordinate system. We're going to let the positive y direction be north and the positive x direction be east because it's what we're used to. I have a cat who's running 5 meters eastward, so I'm going to go over here and I'm going to start at the origin. That's the easiest way to start. And I'm going to say that each block, or how about 2 blocks, is equal to 1 meter. And I'm just going to count over 10 blocks. And then draw the tip of the vector pointing eastward. So my vector represents motion of a cat 5 meters to the east. On the other hand, let's say the cat goes in the other direction, 5 meters to the west. Again, I'm going to let the positive y-axis be north and the positive x direction be east. West then would be along the negative x-axis, so if we say that 2 blocks is 1 meter, I'm going to go from the origin, count over 2, 6. That's about 12, looks like it. This would be 6 meters to the west. So again, notice that the arrowhead is pointing in the opposite direction along the negative x-axis. A little bit more complicated example. Here we have a cat that's running 10 meters, 70 degrees west of north. So that's a common way that they are going to express direction in your textbook, even though this is not an angle given with respect to the positive x-axis. We can kind of figure out what they mean by this. West of north would be pointing in the second quadrant. So we're just going to, since I don't have a protractor, I'm just going to estimate 70 degrees to the west of the positive y-axis. So let's say this is about 70 degrees here. So I'm going to sketch my vector, again, starting from the origin, and then pointing upward at that angle for approximately 10 meters. Again, this is an estimate right now. I'm just drawing this to give you an idea of what this would look like. This here would be 70 degrees. If I was going to be indicating the direction with respect to the positive x-axis, well, that would be 70 degrees plus 90. Or 100 degrees. You could also say that as well. Another kind of quantity that we use in physics is something called a scalar. Now, scalar is a lot like a vector, only a big difference is that scalars do not have direction. Now, some examples of this include things that you're really familiar with, like length and volume, height, mass is one that we use a lot, and also time. Now, I'm going to specify that time is a scalar because time is always positive in physics class. If you ever find that your answer gives you a time that's negative, that is wrong. Even though in movies we can go backwards in time, we cannot do that in reality. So never end up with an answer where your time is negative. Time is a scalar, as is mass. Mass is not negative, even though some people would like it to be if they're on diets. Okay, some common examples, ones that we're going to use in physics class a lot: velocity, force, acceleration, and something called displacement, which I'll talk about a little more in a minute. Displacement means change in position, and again, it can be in some direction. You could have a displacement to the west, to the east, to the north, for example. The units that we're going to use are the SI units: meters per second for velocity, meters per second squared for acceleration, newtons for force, we'll see that a lot, and meters for displacement. Now, don't panic about this, but there's some things that you really need to think about when you're doing calculations in physics, especially in the beginning of the year when we do kinematics. There are some quantities that have exactly the same units as vectors, and they seem like they should be exactly the same thing as the vector quantity, but actually they're scalars, and they include distance and speed. Now, speed is a lot like velocity, only speed does not indicate direction. Distance and displacement, there's a little bit more of a difference here that's harder to see. Let's take an example. Let's say we take the same cat. The cat is running 5 meters to the east and then 4 meters to the west. If we add up the distances that were traveled and we ignore the directions, the total distance that was traveled is 9 meters. It's just the sum of the two individual distances. However, if we treat these as vectors and we include the directions, well, then we can figure out that we get a different answer for the displacement. Displacement is the overall change in position. Symbol would be delta x, delta for change. The cat goes 5 meters east, so we're going to count over 5 meters. Let's say 1 block is a meter. So that's the first distance. And then 4 meters to the west, we're going to start at the tip of this vector and count backwards. If we look, the difference between the starting and the ending position is 1 meter to the east. These numbers are different. The displacement indicates the direction of motion overall. So be careful. If the question asks you for a distance, that's not the same as asking for a displacement. Distance is not a vector. And that's the end of the first vector installment for this series of lectures. Thank you very much for watching. I hope you enjoyed them. Stay tuned for the next installment.
Flight 209er, you are cleared for takeoff.
Roger. Huh?
LA departure frequency 123.9er.
Roger. Huh? Request vector. Over. What?
Flight 209er, clear for vector 324.
We have clearance, Clarence. Roger, Roger. What's our vector, Victor?
Howard radio clearance, over. That's Clarence, over. Over. Roger.
Huh?
Roger, over.
What? Huh? Who?